You see, to understand multicasting, I would like to take one example, which you already know what it is. You see, you have a switch to which you got some routers connected. See, I have drawn a layer 2 switch. What does that mean? That means that these routers are in same VLAN and same subnet. Let's say 10.1.1.1, 10.1.1.2, 10.1.1.3, 10.1.1.4, 10.1.1.5. Please watch carefully, listen carefully, closely. We have these routers, 5 routers. Router 1, router 2, router 3, router 4, and router 5. Now these 5 routers, they need to discover each other when you run what? A routing protocol. Let us take OSPF. OSPF is a routing protocol that works on IP network layer. You don't have any TCP. You don't configure neighbor manually. The neighbor discovery happens automatically with the help of hello packets. They introduce themselves to others and others introduce themselves to us, to this. So the routers send hello packets. The hello packets in OSPF, which is sent every 10 seconds, helps to know each other, learn neighbors, and with the neighbor, the route updates are shared. Link state updates are shared. DBD is exchanged. This is the story how OSPF forms adjacency. Likewise, other routing protocol. Not only routing protocol, there are many services that forms a group by sending hello packets and work as a group after they form a group. So to form a group, you need to send hello packets. To identify group members, you see, if one router is advertising, I belong to area 2, the others are all advertising saying, I belong to area 3. Will R1 be part of area 3? No. But R1 also sends hello packet. R1 sends hello packet. R2, R3, R4, R5 will receive the hello packet. But there are certain parameters that are supposed to match is not matching, so they don't form a group. R3, R4, R5 and R2 forms a group because they belong to common area. But when a packet is sent by R1, R2, R3, R4, R5 receives it. Same way, when a packet is sent by R2, R3, R4, R5, R1 receives it. Why? Because it belongs to OSPF group. They all belong to one group called OSPF, inside which R1 is area 2 subgroup, R2, R3, R4, R5 is another subgroup called area 3. That is another separation. But basically, all 5 routers are OSPF routers. Whereas this router, which is R6, will never learn any packets, will never receive any packets, because this don't belong to that group called OSPF. This belong to EIGRP. So R7 and R6, they never learn any neighbor which don't run EIGRP, because R7 and R6 have formed another group. Though they belong to same layer 2 domain, they may even have 10.1.1.6, 10.1.1.7 as IP address. Even though they are in same subnet, they are in same VLAN, the hello sent by R6 and R7 never received by 1, 2, 3, 4, and 5. Why? Because they belong to another group, OSPF group. They never receive, they never accept, the packet coming from EIGRP. Whereas the packet coming from R3 is accepted by R1, but it won't take it as neighbor. That's OSPF policy. Why? Area ID mismatches. Whatever R1 send, R2 will receive it, accept it, read it. While reading, it knows that according to policy, I cannot form neighbor with this guy because R1 belong to area 2, I belong to area 3. So they don't form neighbor. But the hello packets that are sent from R1 were received by R2, 3, 4, and 5, not received by 6 and 7. 6 and 7, they won't even open the packet. They won't accept the packet inside. They'll say, I don't want. But whatever R3 sends, R1 will receive it, R2 will receive it, 4 and 5 will also receive it. They'll open it, they will process it. And R3, 4, and 5, 4, R3, R4, R5, and R2 forms neighbor because they belong to one common area, and R2 don't form neighbor with these guys. But still, the hello packets that are sent between this R1 to R5 will be received by them. But the hello packets that are sent from this group member will never be accepted in other group called 7 and 6 because they belong to EIGRP, another multicast group. That's what I want to say now. How R1, R2, R3, R4, R5 can form a group even though they belong to different area? Because you're running OSPF on all of them. That is how they form a group. Because you run OSPF on all this router, they form a group. How can OSPF form a group? When you enable OSPF, a multicast group called 224.0.0.5, this all 5 routers will join, enroll, sign agreement. R1, R2, R3, R4, R5, they join this group, multicast group 224.0.0.5. And the hello packets are sent to this address with a TTL of 1, which means all those routers that are in same VLAN only can receive it. See, if they are in different VLAN, they are in different broadcast domains, so they cannot be in one hop away. So for R1, for the router R1, R3, R4, R5, R2, they're all in single hop. Even R7 and R8, R7 and R6 is also in one hop. So the packet that is sent by OSPF will be touching the ports of R6 and R7, but R6 and R7 will not accept it. Whereas the ports of R3, 4, 5, and 2 will accept it, they process it. After processing, they ignore it because R3, R4, R5, and R2 belong to another area called Area 3. That is OSPF rejection. Whereas when R1 sends a hello packet, R7 and R6 rejects this. It's not because of the routing protocol policy. It is because of different multicast group. R7 and R6 are not ready to receive any packet that is sent to a multicast other than 224.0.0.9. Sorry, 10. AGRP is 10. So any packet that is sent to this 224.0.0.10 only, R7 and R6 are ready to welcome in. R6 and R7, when they find another packet, means a packet with different multicast address, they say this don't belong to me, so we don't welcome this. We won't read the packet. So the hello packet sent by OSPF router, they go and touch those EIGRP routers, no doubt in it. Because the hello packets are sent with TTL of 1 and they're all in same broadcast domain, but they don't process it. Yeah. So multicast group is what reason, a secret, the logic behind routing protocols forming neighbor. It's a multicast address. See, if I want to form neighbor, I need to know his name is Joseph. His name is Sheikh. Only when I know the name, I will say, hello Sheikh, how are you? Hello Joseph, how are you? I can say hello when I know the person. If not, I cannot form neighbor. I know the name of a person, at least I know the face that he belonged to this place, this street. So when I say hello, he is ready to accept my hello and I am ready to accept his hello back. We cannot simply say hello to someone on the road. They won't accept it inside. They won't welcome it because they know we don't belong to them. So when you send hello packets to 224.0.0.5, R7 and R6 don't welcome it. It say, hey, I never seen you in this area. Who are you? Who are you, man? Wearing different kind of weird dress. My country people never wear dress like this. You are wearing shirt below the hip, pant above your hip. You are very funny, man. We don't wear like this. We wear opposite. We wear pant down and the shirt on the top. So I cannot be your neighbor. Um, you see? Likewise. The reserved multicast address helps to send a packet to a destination address. So you don't know the IP address of R3, R4, but still you can talk to R3 and R4. It is because you have a multicast address reserved for OSPF, and all those routers that belong to OSPF are ready to receive packets sent to 224.0.0.5. When a packet is sent to 224.0.0.5, the packet goes to everyone here within this layer 2 domain. But R3, R4, R5, and R2, what it says is, it says, I accept this packet because the destination of the packet says OSPF group members. The packet that is coming from R1 with the destination address to 240.0.0.5 says, oh my dear OSPF beloved brothers. That's why we accept this packet. So EIGRP routers, they say, what? OSPF? I'm EIGRP. Not for me. Don't come to me again. R7, R6, they don't accept the packet. Who? 224.0.0.5. Who are you? So this is how the routing protocol, even though they don't know the neighbor's IP address, they still manage to form neighbor, establish neighbor using this multicast. If no multicast, it is not possible for dynamic discovery of neighbor. You have to configure neighbor manually. So dynamic discovery of neighbor is possible because of multicasting. Multicast addresses are class D addresses. Class D range of address ranges from 224 to 239. So this range of address is only meant for multicasting. This range of address you cannot assign to any device as a device identification. It is only for group identification. Devices that have got common something like common OSPF or EIGRP, something in common, or an application. You know, you have if you have a intranet messenger group for all the HR, they give a multicast address. So all the HR devices, they can interact each other because they got one common multicast address. They no need to say, I'm sending this message to that HR. Anything you put in that messenger, it will go to all HR members in that office because they all belong to one common multicast group. For every department, you can have one multicast address, and the application that provides you the service will not allow any message to leak from one multicast group to another multicast group. Not possible. Anyway, that's the job of the application. So I'm trying to give you an example for multicasting. That's all. So messenger is one. This 224 range is a reserved range. See, here we saw 224.0.0.5, 224.0.0.10. Like there's various protocols and well-known applications have got some reservation. Rest all we can use. If you are developing an application within an organization, if you're going to use, then you can use any multicast address that is not in use in your organization, any multicast address. But if you're going to develop an application that you want to sell to the entire world, then you need to buy one multicast address for your application. From the reserved multicast pool, they will give you one address. Whatever I have said for this many minutes, spoken this many minutes, this is not syllabus of multicasting. This one, an example where all we have seen multicasting before. OSPF, you have seen EHRP, you have seen. Before starting MPLS, I thought of telling you how this multicasting is used in routing protocols, which we already know. Now we are going to actual understanding multicasting. See, the routing protocol uses multicasting, and if you notice, the TTL is only one, which means they cannot form a group with those devices that are more than one hop. They need to be within a LAN. So this example that we saw, can OSPF form neighbor with a 10th router, 10th hop? Not possible. For that you need TCP protocol like BGP. So the scope of multicast here is only one hop, within a hop, not even one hop, within a hop, within the LAN. But the multicast that we are going to learn is bigger than what you have seen here with the routing protocol. The multicast that we are trying to have is like this. You got many routers. I'm just randomly drawing, okay? There is no logic here. Now to all these routers, there are many computers here and there connected. I'm just drawing computers as dot. There are many computers. And some of the computer runs this blue application. Now I want to form a group, blue group, blue group. But see, these group members are not in same local area network. They're in various part of the topology. They're in various part of the topology. So How are they going to form a group? If anyone wants to send any packet from this source and destination is blue group, how it is going to happen? So whenever the source send a packet to blue group, it should be received only by those 4 members. Blue, 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 blue. No other computer should receive it, or no other network devices should receive it except this 4. For this you need multicasting. Okay, before getting into multicasting, can I use unicast? Yes, you can use unicast, but you remember, for unicast you need to know the destination's IP address. So those 4 computers' IP address you should know. Otherwise, unicast is not an option for you. Not only that, because you have 4 different destinations, the packet that you want to send, you need to send it to 4 different address now. So 4 times you are duplicating the packet, because the packet needs to go to 4 different destinations. Though the message is same, you need to duplicate it 4 times and put 4 different addresses and send. So the problem is more traffic, more bandwidth, more process utilization, because in the middle all the routers need to process all 4 packet and send them to 4 different direction. Bandwidth utilization, process utilization, you need to know the destination IP address, meaning those 4 IP address of those 4 devices. Only then the source can send the packet to all the blue members, otherwise not possible. So unicast is not good whenever you are trying to talk to a group of people. Unicast cannot be an option. What about broadcast? Broadcast also cannot be an option. Why? If you do broadcast, not only that blue computers, everyone is going to receive the packet. So broadcast is also not an option. See, broadcast is going to take less amount of bandwidth. Why? You are sending the packet to one address called broadcast address. So bandwidth utilization is less, but the problem is it is going to everyone, and because the destination address is broadcast, everyone will open the packet now. Why? In the destination of the packet you have said, whosoever receives this message, you can own this packet. That's the meaning of broadcast address. Whosoever receives it, this belong to them. Yep. But when you send it to a multicast address like 224.0.0.5, it means only OSPF router can take ownership of this. Now EHRP router says, I'm not OSPF. I won't take this packet. OSPF router says, yes, I am member of OSPF. Let me open this. You see, broadcast is going to deliver the packet to everyone, and no one will reject it because it is sent to a broadcast address. All will open the packet, and they may not be interested in those packets. They will drop it after processing. Waste of process utilization, bandwidth utilization. So, unicast is not an option. Broadcast is not an option. Multicast is the only option. When you send a packet to a multicast address, let's say 239.1.1.1, that is the destination address of blue group. From this source, let's say 1.1.1.1 computer, I'm sending a packet to this destination address. And I have a blue member here, 239.1.1.1. So all these guys only will be receiving the packet. No one else can open that packet. And the number of packet that is sent is only one, not five. And the sender will not know really how many are there receiving our packet. Sender will simply send it to 223, 239.111, 239.111. Whoever has joined that multicast group will be receiving the packet. Number of packets sent is one, but the number of receivers may be thousands, because those thousands might have subscribed. Because they subscribed, they got the multicast address configured on them called 239.111. See the advantage. Okay. Now, how is this possible? In the routing protocol example, they were all in single local area network. But this is not in single local area network. There are many routers. How will this multicast packet reach from here to here and here and here and here? How will it go? There is a protocol called PIM, Protocol Independent Multicasting. PIM. The protocol independent multicasting will carry the multicast packets. If no PIM, not possible to carry the multicast traffics from one LAN to another. No. Yes, please. We have to configure PIM on every link in the path. Every link in the path. Now, PIM is one protocol. Now, there is another protocol called IGMP, which is helping to join this group. Whoever wants to receive, not send, whoever wants to receive the packet, they need to join the group. To join the group, this computer, if it wants to receive the packet, which is sent by S, then it needs to join the group by using a protocol called IGMP, Internet Group Management Protocol. Right. So I have explained to you how this multicasting works in a very easy way, and the protocols involved in multicasting. To join the group, I need a protocol to say I belong to this group. See, in OSPF joins the group by using a similar protocol. You don't need to do anything as a multicast configuration. Whereas here, We don't have any protocol. It's our own multicast service that we are trying to have. So you need these things to take the multicast packet from one network to another network, one LAN to another. You need PIM. For the members to join the group, you need another protocol called IGMP. What we are going to see in the next class is the different type of PIM, the different versions of IGMP, and then a lot of PIM variants, and there is also something called RPN, auto RP, and many more things. Anycast RP, BSR, which we'll discuss first of all what they are, and then we'll get into those things. So this is what in our coming days we are going to see. But whatever I have delivered today is the most important. This is the cake, layered cake. All those that coming next is the cream on the top of the cake. Yep. See, am I sounding like a bakery owner? Fine. Thanks for joining. See you tomorrow. Good day. Welcome.